See Standard 12th Maths Chapter 2 Complex Numbers Exercise 2.7 Question number 3. Question is if x1 plus I y1 x2 plus I y2 x3 plus I y3 xn plus I yn is equal to a plus ib. Show that the first division is x1 square plus y1 square into x2 square plus y2 square into x3 square plus y3 square xn square plus yn square is equal to a square plus b square. So let me do the first subdivision, then we can come to the second one. So just first write what is given. Given x1 plus I y1, x2 plus I y2, x3 plus I y3, xn plus I yn. This is equal to a plus ib. It's given for you. I am going to prove this, the first subdivision. For this, taking modulus on both sides, taking modulus on both sides. So modulus x1 plus I y1, x2 plus I y2, x3 plus I y3, xn plus I yn. This is equal to a plus ib, modulus a plus ib. So what is the modulus of this complex number? This is equal to root of x1 square plus y1 square, root of x2 square plus y2 square, root of x3 square plus y3 square, root of xn square plus yn square is equal to root of a square plus b square, modulus value. Now I am going to remove the square root. So squaring on both sides. Squaring on both sides. So in that case, when I square each of the term, the square root goes off. So you will get just x1 square plus y1 square, x2 square plus y2 square, x3 square plus y3 square, xn square plus yn square. This is equal to a square plus b square. This is what we have to prove in the first subdivision. Let me come to the second one. I have to prove sigma r equal to 1 to n tan inverse of yr by xr is equal to tan inverse b by a plus k pi, where k is an integer. I have to prove. You take the given statement again. So for proving the second subdivision, again let me take the given concept x1 plus I y1, x2 plus I y2, x3 plus I y3, xn plus I yn is equal to a plus ib. So I am going to take so we need the argument on tan formula, tan inverse y by x. So in that case, I have to take the argument on both sides. Taking argument on both sides. On both sides. So by property, we know the property 2, argument of z1, z2 for complex number So argument z1 plus argument z2. So same thing here, argument for each of the terms. Argument x1 plus iy1 plus argument x2 plus iy2 plus argument x3 plus iy3 dot plus argument xn plus iyn. This is equal to argument of a plus ib. The plus one, you have already learned this in that same trigonometric chapter in plus one. Last exercise, if two tan values, tan theta is equal to tan alpha, then theta is equal to some n pi plus alpha, n pi plus alpha. The alpha ranges in the interval minus pi by 2 to pi by 2. In that case, we can express theta equal to n pi plus alpha. So, what is n? N is an integer here. The same concept you apply here. Here two tan inverse functions are equal. Tan inverse functions are equal. So, in that case, I can write that r is equal to sigma r equal to 1 to n tan inverse of yr by xr is equal to tan inverse of b by a plus some k pi. See theta and so what is k? K is an integer. K is an integer. This is what we have to prove in the second subdivision. So but this is in here from the plus one book. See the fourth sum. If 1 plus z by 1 minus z equal to cos 2 theta plus I sin 2 theta, show that z is equal to I tan theta. We have to prove z value is I tan theta. What is z here? Complex number. So given 1 plus z by 1 minus z is equal to cos 2 theta plus I sin 2 theta. So let me replace this cos 2 theta plus I sin 2 theta in the Euler's form e power I2 theta. This is in the Euler's form, both the same. Now cross multiply. 1 plus z is equal to e power I2 theta into 1 minus z. So that is 1 plus z e power I2 theta minus z into e power I2 theta. You collect all the z term one side and the other terms to the other side. So here one is z term. Let me bring this z term to this side. So z e power I2 theta is equal to, keep this I2 theta in the same place. Take this 1 to the other side, minus 1. Take z as common. So 1 plus e power I2 theta is equal to e power I2 theta minus 1. So therefore z is equal to e power I2 theta minus 1 by 1 plus e power I2 theta. See, for our simplification, we need to get theta. So I don't want 2 theta, just theta I want. Divide each term by e power I theta. Divide each term by e power I theta. So therefore, e power I2 theta by I theta is just 1 e power I theta, one term. Then 1 by e power I theta. This is equal to e power minus I theta. So minus e power minus I theta divided by e power I theta plus, so here 1 by, if I write, this is minus e power I theta plus e power I 2 theta divided by e power I theta 1 e power I theta. So this is the term we are getting. So what about e power I theta minus e power I theta? See, e power I theta is actually cos theta plus I sin theta. E power minus I theta is cos theta minus I sin theta. So if I add, see the denominator term, if I add means, so this is plus, and here you will get 2 cos theta. You will get denominator as 2 cos theta. So z is equal to 2 cos theta. This I sin theta minus I sin theta gets cancelled. Numerator term I need to subtract minus. So change the sign for all the terms. This is minus, this is plus. So what you will get here? Cos theta minus cos theta gets cancelled. You will get 2i sin theta. So numerator you will get 2i sin theta. 2 gets cancelled. I sin theta by cos theta. So what you will get? I tan theta. I tan theta. See the proving part. You are supposed to prove z equal to I tan theta. So we arrive at the answer. So you have to understand all this. Thank you.